Howdy, periodic trends. Here we go. All right. So I've got pulled up a periodic table over here. This is the modern IUPAC, International Union of Pure and Applied Chemistry. This is the modern, up-to-date periodic table. Um, some interesting things about it, and then some little details we're not wild about. So we've got our standard stuff over here. You notice we don't really have the staircase labeled, so you want to know where that staircase is. And we're not quite sure what happens down here. All right. So then you'll notice some kind of wonkiness going on with the lanthanides. They've just got them labeled lanthanides. And instead of there being 10 across here and 14 in the Fs, what we actually have going on is 15 down here because there's been some debate on whether lanthanum needs to be here or we need to put lanthanum down here and Lu up here. That would make the uh, electron configurations a little bit easier. There's no doing the 6s2, 4f14, 5d10 kind of combination. Now you would just roll automatically and not have to remember to come back and pick up lanthanum. But they've got a committee on it. They've written a bunch of books, a bunch of papers, 3 or 4 books, I guess, maybe more. Mostly telling us how hard the problem is. So when they, run out of book ideas, I guess we'll have us a better idea of what's going on with it. Okay. So whatever. We got all kinds of stuff in view in different places. All right, so we're going to be looking at the periodic table. But instead of looking at this one, let's look at the one that's in our book. So this is the one I usually give on tests. I can tell it's quite old. It's not filled in. It's was the original picture was a color picture. Let's see. I apologize. Periodic table. Oh, here's a pretty one. That hey, it's filled in. Look at this nice good book. Let's show you this pretty one. So it's got all kinds of colors and everything else going on. Big bold. You notice they haven't decided what to do down here with our staircase. And they said metals are that way and non-metals are this way. No mention of metalloids or semi-metals. They got lanthanum still over here. Okay. So still some debate on this. This is what? Zumdahl. So this is the Gen Chem 1 book, Gen Chem 2 book currently. So yeah, okay. They also have 8A, and they've got all this. Oh man, no Roman numerals. That's kind of okay. So let me go back. Let's look at this one. So we're going left to right here. First, let's start with the name, periodic table. All right, so let's go ahead and pop over here to this PowerPoint. So the physical and chemical properties are periodic functions of their atomic numbers. In other words, if I take 1 through, let's skip 1 and 2. Let's do 3 through 10. So we'll do lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And if you put a sample of each of those next to each other, and then you do a sample of sodium and magnesium, you start to see these patterns that kind of repeat. They're not perfect, but they're repeating patterns. And a lot of people equate this to the notes in music. And so looking at this, we've got a period is the horizontal row. You want to be careful. So when we look at this kind of thing, the word period goes up and down, but it's talking left and right. And so you can just name the period by first period, second period, third period, and so on. Easy enough. Don't forget the lanthanides and actinides here are actually on period 6 and period 7. This one's nice and got it labeled down here for us. So that makes life a little bit easier. And they've pulled them out specifically so that we could do our electron configurations. And so let's pop us back over to this one. Okay, so groups or families. I like the term family. Group is nice and short, but family describes better what's going on. A family, they share very similar chemical properties, and they slowly change as you move down the group. Okay, very similar chemical properties inside a family. All right, so several different ways of naming these. So let's look over here at my periodic table. This one's a good classical kind of American periodic table. So we've got a couple of different names. All right. First, you can see these 1A, 2A. These things have Roman numerals. So we better review our. So if this is 1, that's 1A. And so this would be 4A and 7A and so on, right? And there would be 9. So make sure you remember your Roman numerals. And we notice this A and B. And so when I look at my periodic table, I see this labeled representative elements and transition elements. And so that's our first kind of dividing lines. Now, what I usually refer to these then, um, this A and B. So B is transition elements. If I can spell it, transition elements or transition metals. All right, and a lot of them will be called because they all happen to be metals. Now, the ones that have an A in the American periodic table after that Roman numeral are representative elements. All right. You'll also hear us old people refer to those as main group elements. That's not a completely acceptable term anymore, just because the people that work in the transition elements, hey, there's more of them. Why are those the main group? The reason why is because some of our trends hold more true, and the patterns are easier for the representative elements. So if I got rid of this label up here that said representative elements, then we would be able to tell these A's over here. But you notice we also have just the 1, 2, 3. And when I went back and looked at the current IUPAC, or even that this other one, they get rid of the A's. And that has to do with this wonkiness going on here. So here's 1A, 2A, 3A is over here. And down here is 3B, 4B, 5B, 6B, 7B. 8B's got 3. What? And then 1B is just, what? So, uh, international system then we'll go into reasons later. It had to do with differences in the Russian and the American periodic table. But so here's the 1, 2, 3, 4, and then you just go 1 through 18. So which ones are the main group elements or the representative elements? That's groups 1, 2, and 13 through 18 if we're just going with that new system. And then the transition here then would be 3 through 12, including the inner transition elements, the lanthanides and the actinides. But those of us that have been doing electron configurations, then is an even easier way of saying this. The representative elements are the S and the P blocks. And the transition elements are the D and the F blocks. And that actually kind of make things a little easier in my head, since I already kind of remembered where the S's and the P's were. This makes life a little bit easier. So splitting those up, those aren't the groups. That's just some information given by the group name. So what are we talking about for the group names? Well, we've got stuff like 4A. Oop, 4A. All right. That same group, 4A, happens to also be 14. So we can call it group 14, group 4A. And then the head of that that group and that family, when I come over here, here's 4A or 14, and the head of that family is carbon. And so this is the carbon family. Okay. So 3 acceptable names for every group: representative, transition. Those are not acceptable names. Those are just categories. The names 14 for A. So it's either the A or the B with the Roman numerals, or it's going to be the group, or it's going to be the head of the family. But there are uh, four of these that we also need to memorize. And so those four are listed up here, where we have a list of the alkali metals. That's 1A, that's group 1. All right. And the alkaline earth metals. How do I remember that? Well, okay. So 2 is bigger than 1. And so group 2 gets a longer name. So the alkali metals over here on the left, alkali metals, alkaline earth metals. On the far side, we've got the halogens in group 17. And then the last one over here in group 18 is the noble gases. Now, it had an older name of inert gases, meaning they do not react. What happens in science is if you make a hard set rule like that, some smartass is going to make it their life's mission to make them react. And we have since made all of those react, just not in conditions we're going to see in our lab. All right. So these noble gases, we had to change the name. Couldn't call them inert gases if they'll react. All right. So noble gases, halogens, over on the left, alkaline metals, alkaline earth metals. Now that means those four have four acceptable names. All right. So when I'm looking over here at chlorine, chlorine is in the halogens. It's in group 17. It's in group 7A. It's also in the fluorine family. Those are the acceptable names for that family, that up and down. Okay. All right. So the other big dividing thing that we worry about, and that's what most of this coloration that we see going on here, is really trying to help us to figure out what things are metals and non-metals. And metalloids is what our book calls it, but I call them semi-metals. So it's actually quite easy. You find your staircase. And so here's my staircase: down, over, down, over, down, over, down. And then we're not sure. This one shows it going down and over. Oh, yeah, we don't have any evidence to back that up down there. So here we go. We've got non-metals over to the right, and the metals to the left. Easy way. These are the alkaline metals, alkaline earth metals. So going towards them, there's the metals. You can also see over here I've got iron and copper and silver and gold, things that we think of as metals. Lead's down here. So those are the metals. Easy enough. Now the things that we associate with metals, so they have certain properties. We have stuff like luster and that's shininess, whether something is ductile. Uh-oh, got myself in trouble. Now I gotta try and spell malleable. That doesn't look right at all. Let's see, what else are we with? They're solids. They are conductors. They conduct heat and electricity. All these kind of things. All right. So we've got those. Where do they kind of fit in? They're over here. These are our metals in. So this is our non-metals. And the semi-metals or the metalloids are touching my periodic table. All right. And so they're touching the top and bottom and side. So corners, wait a minute, you guys can't even see. Let me switch this. Okay. So metals, non-metals. So touching top and bottom, side and side on my staircase, no corners. Then those are going to be our semi-metals or metalloids, whichever word you want to use. I like semi-metal because I'm old-fashioned, I guess. Now you'll notice aluminum here is a different color than these because aluminum is a metal. And so when I look, and I can't show you, but I've got aluminum all over the place here. If I hold up a piece of aluminum, none of them happen to be where I can put them on the camera. If I hold up a piece of aluminum, you would immediately say, hey, that's a metal. That's a piece of metal. Now, aluminum's got some neat properties associated with um, the fact that the further away from that staircase, the more like a metal you are. The semi-metals, think of them as the sort of metals. They have some of the properties of metals and some that aren't. So they do some funky stuff. Okay. All right. So let's look at our trends. So let's let's see. Wait a minute. Let me make sure we don't have anything over here else I need. We'll deal with those later. I want to do our trends. All right. So atomic trends. Atomic trends. It doesn't really matter which book you're in. I've always seen this taught in the same order, and we're going to use that to our benefit. So the first one is atomic size. How big is the atom? The second one is ionization energy. The third one will be electron affinity. And then the fourth one is electronegativity. All right. Now, there are lots of ways of doing these. We could pull them up in tables and look at that and try to get these trends. But the whole idea here is to remember this is kind of like fashion trends. There will be some exceptions. There will be times that we just don't follow the pattern. So, what we want to do is have a nice, easy way to predict these. And so, what I'm going to do is locate two markers. So I'll look up here at fluorine, and I'm going to look down here at cesium. Now, we could use francium being further in the corner. It's just so radioactive, we don't ever encounter it in our lab. So let's use cesium, same kind of idea, all right? And then we've got fluorine up here. You might ask why we don't use helium. Remember, helium and neon don't want to react so much, so we're going to look at focusing on fluorine. All right. Why two markers? Because we're going to be able to judge things, and the overall trends, you'll be able to say, hey, carbon is close to fluorine, or you can look and say carbon is far away from cesium. And you'll notice I'm just drawing a straight line connecting them. I'm not following the numbers. And so if I'd say carbon's right here versus this distance. And so nice and easy. So let's look at these trends. Atomic size. Then we have, I'm going to put cesium and fluorine. Those are my markers. Atomic size, cesium is really big. It's the biggest. And fluorine is small. It's the smallest. All right. And so as long as I remember that the closer I get to fluorine, the smaller I am. The closer I get to cesium, the bigger I am. So if I gave you some elements, let's say I gave you magnesium and beryllium, and I asked you which one would be bigger in size, bigger in atomic size, you would say beryllium, all right, because it's closer to cesium. See how it's a much closer, it's right next to it. All right. Now this can be explained. We can go into all kinds of patterns here about, well, if I increase the number of electron layers and energy levels, that of course we get further out and the atom gets bigger. And then as I go this way, it gets smaller. So the books are full of all kinds of these patterns of as you move down the periodic table, things get bigger, and as I move across, they get smaller. Don't try to memorize any of that. Just cesium is really big and fluorine is really small. So if I pick iron, here's iron, and aluminum, which one do I predict will be bigger? Well, for me, I can come over here to cesium and I can see iron would be a shorter line. And so it would be my bigger one. Now, what if I picked nitrogen and iodine? Now trying to compare over here to cesium might be a little tougher, but I can look over at fluorine and say nitrogen is closer to fluorine, all right? Because it's closer to fluorine, I'm going to predict the nitrogen to be more like fluorine in its properties, and fluorine was small. And so, therefore, I predict nitrogen would be the smaller atom, and then iodine would be bigger. Okay. So that's why we have two markers, so you can go to whichever one is easiest for you to locate. All right, so the next trend then. Let's talk about ionization energy real quick. Oh, I'm sorry, atomic size. If I have a negative charge, that makes things bigger. They'll be bigger than the neutral atom. If I have a positive charge, it's going to be smaller. And the easiest way to think of this is just keep in mind electrons have a negative charge. That was kind of our key for all of this. And so if electrons have a negative charge and I add more electrons, things have to spread out. Okay. So because they repel each other. All right. So that takes care of those. Ionization energy. How much energy we have to pay an atom to pull away an electron. Electron affinity, how much energy the atom releases in order to buy an electron from us. These two kind of go hand in hand, and they follow the same pattern, and I'm actually going to make life easier by just worrying mostly about electronegativity, because it's kind of the atom's desire for an electron. Now, this includes the electron it already has, and it includes electrons gaining new ones. Now, the same patterns show up here. All of these are small for cesium and big for fluorine. So when you're doing these, you have to pay attention to which trend we're looking at, because notice they're all, like I said, these are always in the same order in the books, and so this makes life easiest. They start with the size first, and so it's big for cesium and then small for everything else. Whereas fluorine is small and then big for everything else. So when I was taking my test on this, I'd come over here to cesium out here. I wrote big, small, 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 and I came over here to fluorine and I wrote small, big, big, big. All right, small, big, 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 and then it really is just a matter of if I gave you some elements. Let's say I gave you chromium and bromine, and I asked what. Well, and you guys can't read that too far down. Let's do copper and bromine. Be nice and easier. All right, copper and bromine. So here's copper. Oop, gotta go back to my parent. Here we go. Here's my copper at 29, and bromine's over here at 35. And then I said, hey, which one has the biggest electronegativity? And so we could try and compare them over to cesium, but it's actually closer. Both of them are sort of close to the fluorine. And so bromine is closer to fluorine, so it would have a bigger electronegativity compared to my copper. And so it wants the electrons it has, and it wants to gain a new one, more so than copper. So this helps me kind of help make some predictions. Copper's more likely to lose those electrons. It doesn't really care about them. And bromine wants them. That's kind of going to be our key guiding thing here. If there's a big difference in electronegativity, then there's a difference in desire. All right. I learned this one the hard way. Um, so we're going to stop for story time here. We've got our trends for the most part, how we're going to handle them. So let me kind of illustrate this one for you. Nice little story time. So my oldest son, when he was 2, we took him to his first daycare, and I used to work in daycare, and my wife used to work in daycare, and my mother-in-law used to work. Anyway, it goes way back, all right. And so I knew kind of what to expect and what my role was. But that first day of daycare was always tough. There's so much crying and tears and biting and just kicking and finally I said, honey, calm down, he'll be fine. But so then I got him there, and so drop him off. Oh man, you feel rough, and then you go pick him up, on that very first day. And most of the time, you can tell the new dads, they always do the dad thing. You sneak up and you peek over the window because you don't want them to see you because then they're going to immediately come running. You just want that reassurance that, oh, I'm not an evil person for dropping him off, right? And so I peek over and there he is. He's got a little truck and he's playing his truck, right? And oh man, I'm not a failure. All right. And then a little girl comes over and she says something to him. And I can't hear him through the window, but she says something and he says, no. She says something again. He goes, nope, 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 nope. And so then she does what has to be described as kind of Wolverine's move, something like this. And claws came out, and I don't know for sure what what happened next. It was all just kind of a blur. But the next thing I really saw was he was over here crying, and she's over here playing with the truck. And what I realized was she wanted that truck a whole lot more than he did, and so she got it. And that's going to be our key to electronegativity. The atom that wants it more will get it. It will tend to make then negative charges because it's gained an electron. The atom that didn't want it very much will let that electron go. It doesn't even want it. And so those will tend to make positive charges. And then the atoms that want things about the same, they're going to have to share. Depending on if they want them exactly the same, then they'll share equally. If they, not really, one wants it still more than the other, then they share unequally. If you've grown up with siblings, you know what that's all about. There's no equal sharing. There's, hey, he's bigger, he always gets it. Or, hey, he always cries, so the little kid gets it. Whatever side you're on, you got siblings, you know all about the unequal sharing, right? Uh, So we can also use the same idea here and make some generalizations. And we can say the metals are all going to be closer to cesium than the nonmetals. So those metals will tend to lose electrons. And the metals will tend to gain electrons because they have a higher electronegativity. All right. So we're just about done here with these. We've got some work on some predictions we can make about the bonding, but we're going to save that and we'll end there with this idea of fortrans, and you can tell them by looking at your periodic table. All right, catch you on the next one.